Welcome. We're now going to take a closer look at the t-distribution. But before doing that, I am going to do a little bit of review here on the value of z alpha over 2 when we're talking the standard normal distribution. So I'll be doing an example of a 95% confidence interval. So let me write some detail up here. So as we did previously, we know our value for alpha is 1 minus our confidence level. So I'm going to do the 0.95 case. So that's our alpha 0.05. And then alpha over 2. If we divide 0.05 by 2, that is 0.025. And let me just show you what that represents here on the picture. So for our standard normal distribution, these will be our z-scores. So that solid graph there, that bell curve, that center area represents our confidence level, so 0.95. And then this area in the right tail is our alpha over 2. So in this case, 0.025. And the z-score that makes all this happen is called z alpha over 2. All right, so one way to find that z-score is to inverse norm the area to its left. So that's why after we found alpha over 2, we found 1 minus that value. So 1 minus alpha over 2. So I'll do that on the calculator here. 1 minus 0.025 is 0.975. So our z alpha over 2, we can inverse norm for the normal distribution, that area 0.975. All right, I'll go ahead and do that as well. So back to my distributions and inverse norm 0.975. And there's our 1.96 we've seen before. So I'm going to make a note here on the t-distribution table. The very last row on the table, it says z infinity. So the idea here is that a t-distribution begins to look like a z-distribution as the sample size increases. And another way of saying that is as the degrees of freedom of a t-distribution increases, it starts to become a z-distribution. So the last row of the t-table are actually the z-scores corresponding to various levels of confidence. So we're doing this example, 95% confidence. So that z-score is 1.960, has 3 decimal places there. We have 2, but that is our value. Okay, so let's see how this relates to t alpha over 2 for the same level of confidence. And now because t-distributions change shape based on sample size, I'm going to need a sample size. So in this case, n is 5. All right, so degrees of freedom of the t-distribution is the sample size minus 1. So in this case, 5 minus 1 gives us degrees of freedom 4. And that's what I've shown you over here. So this t-distribution is shorter than a z and wider. So if I still want to have 95% of the area covered in the center because the graph got shorter, in order to keep that area at 95%, we're going to have to go further out on our number line. So I'm just going to draw a dotted line over here. So somewhere out here is our t alpha over 2. All right, so z alpha over 2 was 1.96, and we're about to find out what the t value would be when we have a sample size of 5 with 4 degrees of freedom. All right, so let's do this first, just reading the table. So degrees of freedom, 4, and then we just come over and read our answer. So that's 2.776. And I'm going to just write that down here on our graph. And that is one way to find the t-value using the table. Now, some of you will have an inverse t available to you, but some of you will not. So the TI-83s definitely will not have the inverse t, but if you'd like to check on your 84 if you have it, let's go back to stat. And I went to the wrong place, sorry. Let's go to distributions, inverse norm, and right below it, under inverse norm, if you have inverse t, that's where you'll find it. If you don't have inverse t, not a big deal. You'll have a table here, and it's actually pretty quick just to read the answer here anyway. But if you do have inverse t, I'll go ahead and write down the input here. So t alpha over 2. So on a t distribution, it's not inverse norm, it's inverse t. And our calculator uses a capital T there. The name of the distribution, it's always lowercase t when people talk about the distribution, but inverse t is how our calculator will write it. And then we have to tell the calculator the area to the left, which is our 0.975, or 1 minus alpha over 2, and then comma. Now we also have to tell the calculator the degrees of freedom. All right, so you're welcome to do it this way if inverse t is available to you, and that will give you the same value. And we just round to 3 places to match our table. So 2.776. Okay, so I'll just do one more here. I don't have the picture for it, but number 2, find T alpha over 2 for an 80% confidence interval when the sample size n is 7. So for this one, I'm just going to read the table. So let's just jot down our degrees of freedom. Right, so degrees of freedom, n minus 1. So 7 minus 1 is 6. So T alpha over 2, you just go to your table. 6 degrees of freedom, 80% confidence, and that value will be 1.440. All right, so we'll use t-scores quite a bit later on, but as we move into creating confidence intervals, rather than doing it by hand, we are going to take advantage of an interval on our calculator called the t-interval. So basically, if we are going to construct confidence intervals for a mean, and the population standard deviation is unknown, then in our formula for margin of error, it looks very similar to our previous formula, but instead of a t, we see a z. And here where there's an s, previously there had been a sigma when we had known sigma. So in this section, s, the sample standard deviation, s, is our best estimate for the unknown population standard deviation. All right, so let's take a look at this question. Number 1, a random sample of 16 health maintenance organizations, HMOs, was selected. For each HMO, the copayment in dollars for a doctor's office visit was recorded, and here are the results. So if you wanted to pause the video for a moment, enter your data into L1, that is your first step. And then we'll move forward. All right, under the assumption that copayment amounts are normally distributed, so just pointing out that this is required because when our sample size is less than 30, and it's only 16, so when it's less than 30, we need to know that our parent population, so the population of HMO copays in this case, are normally distributed. So that's just a requirement in order for the mathematical process here to be valid. And then, assuming that is true, find a 90% confidence interval for the mean copayment amount in dollars. All right, so we are estimating mu, population mean. So that's our parameter. And we always ask ourselves, do we know the standard deviation of the population? So in this case, they haven't mentioned sample standard deviation or population standard deviation. So we certainly don't know sigma. So population standard deviation is unknown. And in this situation, we do a t-interval on our calculator. But before we get to that, I do actually want to just write down our best point estimates. So if I wanted to use sample data to estimate mu, my best point estimate would be the sample mean. So the sample mean is the best point estimate for the population mean. And the best point estimate for the unknown sigma, population standard deviation, the best point estimate would be the sample standard deviation. So if you have sample data, you will always know the sample standard deviation and the sample mean. So I just wanted to jot those down quickly here, just running one var stats. So back to the calculator, stat calculate one var stats. And then just to write these down, I'm going to round to one decimal place. So the sample mean is 8.4. That would be $8.4 as a copay. And then S, sample standard deviation, rounded to one decimal place is 2.4. So just make note here that on the calculator, I'm seeing sigma, but that is complete nonsense here. The calculator doesn't know it's nonsense because it didn't read the question. So we know that the data we entered is sample data. So we have no knowledge of what sigma is because we haven't collected data from every single HMO, the population. All right, so S is the relevant value there. All right, so let's go ahead and find our confidence interval. Now, because we do have the data in the calculator, I don't want to use these rounded numbers when I do my t-interval. So we'll go to our t-interval. So stat, tests, and right below z, you'll find t. And I have data, so you want to move over to data. Now I'm going to make a note here, though, before I hit data, you'll see that the calculator automatically put in my X bar and my S in those positions, but that's only because I ran one var stats first. So I'm just writing over here that in general, if you're making the confidence interval, you wouldn't have to do one var stats first. So the calculator wouldn't be aware of those values. So when we're given data, you always want to switch yourself over to data. And then list is L1, frequency will always be 1. Confidence level was 90%. And calculate. And we'll stick with rounding here to one decimal place. So that's 7.4 lower limit, less than. And the parameter I'm estimating is mu. And the upper limit there will be 9.5. All right, so I can now say that we estimate with 90% confidence the true population mean for a doctor office visit copay for all HMOs. So based on these 10 or 16 HMOs, I conclude that for all HMOs, the mean copay is somewhere between 7.4 and $9.5. Okay. So the most important thing here is we move forward and read questions. When we're estimating a population mean, we ask ourselves if we know population standard deviation or not.